Hello, I am Václav Novotný and welcome to the tutorial of energy sources and conversions. This tutorial will be focused on waste heat recovery and specifically waste heat recovery with organic Rankine cycle systems. We will also show the difference between simple and recuperated cycle and difference between various formulations of efficiencies. Before we start with any calculation, let's have some brief introduction of what the organic Rankine cycle is. So basically it's alternative to regular steam Rankine cycle when we want to have application of low power output or some application at low heat source temperature. It's a cycle similarly like Rankine cycle with external heat source, so it can be applied to systems with solid fuels combustion, geothermal applications, or especially waste heat recovery where the organic Rankine cycle, abbreviated as ORC, is very favorite. The power range of these systems goes basically from really micro systems of, let's say, some domestic size around 2 kilowatts up to 10 megawatts where the largest systems are used in typically geothermal applications. As the name says, the working fluid is based on As the name says, the working fluid is organic based. Typically there are used refrigerants like hydrofluorocarbons and hydrocarbons, working fluids that we have had in the last tutorial, or some, for example, silicon oil based fluids, as we will have calculation with one of them called hexamethyl-disiloxane. The design of these systems is typically purposed to be. These systems are typically designed to be rather simple, with hermetic design, so there is no feed water heating through turbine bleed, and very often for the low power outputs there are volumetric expanders. If there are used turbines, also the number of turbine stages is typically much lower than in the large steam cycles. Very often the working fluids are so-called dry. We can see that here on the right hand side figure, where we have the saturated liquid curve, and which looks quite normally, but then from the critical point, when we have a look at the right hand side of the vapor dome, at the saturated vapor curve, so we can see that it actually goes slightly backwards. So that means that if we have expansion going isentropically from certain point of saturated vapor, let's say from over here, so unlike in the steam where we would go into the wet steam, here the expansion goes into the superheated vapor. So these cycles typically don't need very large superheating, typically just few kelvins in order to make sure that the working fluid entering the turbine or expander is dry, that there are no liquid droplets. Also, this dry working fluid allows for so-called recuperation, because as we can see, if we have the one isobar at the expander inlet and other isobar at the expander outlet, so the expansion from points 2 to 3 would end up with temperature significantly higher than is the temperature of the condensation. So we can actually take some of the heat from here and transfer it to the working fluid after the pump, and therefore we do not need to use that much heat for the heat input. So the heat input from being all the way between points 1 after the pump and 2, we will have just the difference between points 9 and 2. Here on the top we can see how it's made. So after the expander, the working fluid, the vapors still have rather large temperature. So we route them into a heat exchanger that transfers this heat to the working fluid going out from the pump. And then, once the heat is transferred, up to the point of some minimum temperature difference between condensation and minimum temperature difference between point 1 after the pump and the vapors, unless also smaller part of the heat gets rejected in the condenser. So we save some heat from the heat input, and we have the lower heat rejection in the condenser. Also one other feature making ORC suitable for waste heat recovery application is that the ratio of the evaporation heat and the specific heat capacity is much smaller with some of the organic fluids. So for example, if we would have temperature heat diagram of the heat transfer, so for the heat source is cooling down, let's say like this. And if we have the regular water, so it has very small Cp compared to the evaporation heat. So the temperature heat diagram would look something like this to get from x equals 0 to steam quality 1 at the outlet of the heat exchanger. On the other hand, when we have the organic fluid, so if we have the same pinch point, so the graph can easily look like this. So actually the amount of heat that is extracted from the heat source and that can be transferred into the cycle to convert it to work is this large. While for the steam cycle, the heat transferred into it is smaller, as we can see in here. Now let's go for the example of the organic Rankine cycle in waste heat recovery that we will calculate. So we will compare parameters of steam cycle with the water and organic Rankine cycle with 3 different working fluids: Toluene, the silicon oil based hexamethyl disiloxane working fluid, and the R245FA refrigerant. We have given the heat source, which will be air, with the mass flow rate 1 kg per second, and temperature being 350 degrees C. The specific heat capacity of this air will be constant for simplicity, and it will be 1.005 kilojoules per kilogram in Kelvin. Now, what will be the parameters of the cycle? The turbine inlet temperature will always be 220 degrees C, and the condensation temperature will be 40 degrees C. We will assume that the ambient air is at 20, so there is some minimum temperature difference for that. Also, at the turbine inlet, we will consider the steam to be at point of saturated vapor line, except for one case, which will be the water steam with given evaporation pressure, and therefore expander inlet will be a superheated vapor. Also, for the organic Rankine cycle, we will see what will the parameters be when the recuperation would be applied. And for the cycle assumptions, so all the cycles will be ideal. Therefore, 100% efficiency of expanders and pumps, no pressure losses. We will also neglect for simplicity the temperature increase in the pump, and we will not have any subcooling of the condensate. The subcooling of the condensate was this part between the condensing temperature and the 0.5 at the pump inlet. So it will not be in here. And in all heat exchangers, there will be the minimum temperature difference, delta T min, 25 kelvins. And the task is to determine efficiency of the cycles, both simple and eventually, if possible, recuperated. Then the absolute work output of the cycle in the units kilowatts. Not just unit work in kilowatts per kilogram of working fluid, but also we will calculate for the given heat source parameters the absolute power that we can get out of it. For the efficiency, we will not just calculate the efficiency of the cycle, but also efficiency of utilization of the heat source. Because the heat source contains some constant amount of heat, we will say that the Q of the heat source is the amount of heat that we could extract from it if the temperature would be decreased to ambient. So it would be mass flow of the heat source fluid times the enthalpy at the inlet minus enthalpy at temperature being ambient temperature. And also we will calculate the outlet temperature of the heat source stream, which will also show us how much of this theoretical potential our cycle can actually utilize and convert it to work with its efficiency. So we will start with the Rankine cycle and we will draw it in the TS diagram. So the Rankine cycle had, or all the cycles have, condensation temperature of 40 degrees C over here. Then let's call this point as point 1. Then there is the pump going to the point 2, where we actually said that we will neglect the temperature difference, but here we will illustrate it. So we have a pump and some process going from point 1 to point 2. Then we get to the point of saturated liquid in some heat exchanger. So we have the heat exchanger where there is heat input and somewhere within the heat exchanger there is that point of saturated liquid. Let's call it as L. Then we get through the heat exchanger to the point of saturated vapor, which is the outlet of this heat exchanger for most of the cycles, so it would be point 3. Then expansion in turbine or some other expander that converts the pressure potentially into work. To the point 4, where the point 4 is at the pressure of the condensation, which was at temperature of 40 degrees C, and for ideal cycle it would look like this. Where between points 4 and 1 the heat is rejected in condenser. So except for the temperature level 40 degrees C, we also had temperature at the turbine inlet, meaning at the point 3, which was at 220 degrees C. This was the first case of the cycle with the steam. Then there was the second case where actually the evaporation takes place at lower pressure and the steam going to the turbine is superheated. So still we would have this temperature limit over here, but there will be lower pressure difference. So the point 2, let's draw this cycle in green, will be lower. Then again there would be some point of saturated liquid, evaporation, superheating, so that we get at the same temperature, and then expansion in the turbine to the point 4, which will be over here, and heat rejection back to the point 1, which will be same for both cycles. Now let's draw a table with the parameters in each node of the cycle. So let's start with the blue cycle, with the working fluid being water. And then we have the nodes 1, 2, we will also need a saturated liquid, 3 and 4. And we will have pressure, let's use megapascals, temperature in degrees C, enthalpy, kilojoules per kilogram in Kelvin, entropy, kilojoules per, here kilogram in Kelvin, and the enthalpy is just kilojoules per kilogram. And lastly, steam quality X. So what do we know for the cycle? We know the temperature at the point 3. It was given in the problem statement that it was 220 degrees C. And temperature of the condensation, which is temperature at point 1, which was 40 degrees C. Then we actually said that we will neglect the temperature increase in the pump. So here would be also about 40 degrees C. And you can see that the point 4, because water is wet fluid, will be in mixture of steam and liquid, or vapor and liquid, so here at the point it will be also 40. And since the evaporation also takes place isothermically, so the point of the saturated liquid will be at 220 degrees C. Then we know that the steam quality at the point 1, or liquid quality, steam quality will be 0, it will be liquid. Then at the point 2 it's subcooled liquid, it doesn't make sense to evaluate quality. But saturated liquid, so the steam quality at point 1 is 0, it's saturated liquid. At the point 2 it's subcooled liquid, so it doesn't have a value. At the point 3 we again, or at the point of saturated liquid, let's call it like this. Now the steam quality at the point 1 is 0 because it's on the point of saturated liquid. Then at the point 2 it's subcooled liquid, so it doesn't have a value. Point 3 it already says saturated liquid, so we get at the higher pressure back to steam quality of 0. And at the end of evaporation, point 3, the steam quality is 1. Now, for most of the points, or for actually 3 of the points, we already have 2 thermodynamic properties, temperature and quality. Here, here, and here. So for these points, we can use these 2 parameters in either thermodynamic functions or in enthalpy-entropy diagram of water and steam in order to get the remaining parameters. So the condensing pressure at 40, which corresponds to 40 degrees C, or if we find in the enthalpy-entropy diagram point of isotherm 40 degrees C, and it will be at saturated liquid, meaning we would need to go there from saturated vapor, or we can also get the value for saturated vapor. So we would get 7.4 kilopascals, 0.00738 megapascals. This is also the pressure at the point 4 over here. Now, at the point saturated liquid, or point 3, we have also steam quality, we have the temperature, so we can get the pressure from the temperature and being at the saturation line. And the value of the pressure will be 2.32 megapascals. And this pressure at the point 3 is because we don't have any pressure losses, pressure drops, so same as point SL and point 2. Now, for some of these points also we can get the values of enthalpy. So the easiest also with the diagram would be the enthalpy at the point 3, because it's the area which is shown on the diagram, intersection of the vapor line and of the isotherm or isobar, and we will get the value of enthalpy being 2800.95 kilojoules per kilogram. When we have this point, also we can get entropy for that, which is 6.284 kilojoules per kilogram and Kelvin. Now, from this point and enthalpy at some specified quality with the diagram, or from the thermodynamic functions using the steam quality and the temperature or the pressure, we can get the enthalpy at saturated liquid at the high pressure, which is 943.58 kilojoules per kilogram, and eventually if you want to get entropy it would be 2.517, but here we don't really need that entropy that much. And we can also get the values at the in the same manner at the point 1. Also, either from the diagram we get the value at the saturated vapor and value at some specific steam quality, or we use thermodynamic functions where the input would be the steam quality 0 and either pressure or temperature. And the enthalpy would be 167.5 kilojoules per kilogram, and the entropy 0.57 kilojoules per kilogram. Now, at the point 2, after the pump, it's the ideal pump, so the entropy stays the same. And if we have the thermodynamic functions, so we can directly get the entropy and pressure to get the enthalpy. If not, we could use, for example, steam density and pressure difference, while the pressure difference divided by density, or pressure difference times unit volume, would be the work of the pump, and enthalpy at 1 plus work of the pump would be quite precisely enthalpy at the point 2. So the accurate value from the thermodynamic functions, entropy and pressure, is 169.9 kilojoules per kilogram. And for the enthalpy after the turbine, again it's isentropic change for the ideal turbine, and this point is in the diagram. If you are using those, so you find the point of the pressure, or the isobar of this pressure, intersecting with this value of entropy, and the value of the enthalpy will be 1956.1 or 0.12 kilojoules per kilogram. And also we can get the steam quality, which is 0.743, which is actually pretty low for some turbine to actually survive with this. Perhaps some volumetric expander could handle that, but turbines basically not. But this is theoretical calculation, so we will say that the turbine would be able to stand this. Now let's calculate the unit heat input, which is enthalpy at point 3 minus enthalpy at point 2. Which will be 2631 kilojoules per kilogram. Then the rejected heat would be enthalpy 4 minus enthalpy 1, 1789 kilojoules per kilogram. The work of the pump will be enthalpy 2 minus enthalpy 1, which is 2.3 kilojoules per kilogram. And work of the turbine would be 844.8 kilojoules per kilogram. So from this we can obtain the efficiency of the cycle, which is, well, we have multiple options how to get it, but let's say work of the turbine minus work of the pump divided by heat input, and we get 32%. But now, how does this go with the specified heat input that we have? Or rather specified heat source that we have. Well, let's have additional points in our table. Where we will have the heat source inlet, this heat source inlet, which had the temperature of 350 degrees C. And let's have a look how the QT diagram will need to work. So in the QT diagram, where on the y-axis we have the temperature, and on the x-axis we have the transferred heat in the heat exchanger, this heat exchanger over here, the cooling of the heat source will look like this, straight line. And the heating up and evaporation of the steam will look something like this. So here we have the point 2, point SL, and the point 3. While on the heat source side, here we had the heat source in. Then over here, directly vertically on top of the saturated liquid, there will be the minimum temperature difference, or there will need to be the minimum temperature difference, and this point with the same transferred heat between points 3 and SL. So from the heat source in, we will call this heat source pinch point. And then over here we have the heat source outlet. So here we had the heat source in. We don't really need to get the pressure or the entropy or actually even the steam quality. And for the enthalpy, since we have constant specific heat capacity, so we can have some proprietary enthalpy, which we would call, let's say, temperature times the Cp. So this was the point heat source in. Now let's have a look at the heat source pinch point, where the temperature is, since we have specified the minimum temperature difference, so it's temperature of the steam at the saturated liquid over here, 220 degrees C, plus the minimum temperature difference, 25 degrees C. So temperature SL plus delta T min, which is 255 degrees C. Again, the enthalpy, temperature times Cp of the heat source, our own proprietary enthalpy, as we decided that we will have it all referenced to the temperature 0 degrees C. Then we would have heat source outlet. We don't know about that anything yet. And at the last point we will have heat source 0, or so-called dead state, which will be what would happen if we cool down the heat source to the temperature of the ambient air, 20 degrees C. And now, since the heat transferred between points 3 and SL, and heat source in and heat source pinch point must be the same, so let's write the calorimetric equation. So Q, let's say SL3, is mass flow rate of the heat source times the Cp of the heat source times the temperature heat source in minus temperature heat source pinch point. So it will be 1 times 1.005 times 350 minus 255, and this will be 105.5 kilowatts. And since it's the heat transferred between points SL and 3, so it also must be the mass flow rate of the steam, or generally of our working fluid in the cycle, times the enthalpy difference H3 minus H saturated liquid. And the only unknown that we have here, since we already know the value of the heat transfer, so it's mass flow rate of the steam. So therefore we can get from this the mass flow rate of the steam, which will be 0.0 0.0568 kilograms per second. So we could also add the column for the mass flow rate. Where we just calculated that everywhere in the steam cycle the mass flow rate is 0.057 kilograms per second. And we had before specified that for the heat source it's 1 kilogram per second. Now what we are missing is the parameter, the temperature for the heat source outlet. So now when we have the mass flow rate of the steam, we also can calculate the heat input into the Rankine cycle. Because we can calculate it, for example, as the mass flow rate of the steam multiplied by the enthalpy difference 3 and 2, or also directly the Q in. And we can get that the heat input into the cycle is 149.48 kilowatts. And from this, because the heat input into the cycle also has to be the heat which is transferred from the heat source, so it's also the mass flow rate of the heat source multiplied by the enthalpy difference heat source in minus enthalpy heat source out. Which is, mass flow rate of the heat source is 1 kilogram per second multiplied by, and now the enthalpy of the heat source is specific heat capacity, Cp times T. So it's 1 times Cp, let's have it generally, heat source times specific heat capacity, if we assume it as constant, multiplied by temperature in minus, or temperature heat source in minus temperature heat source out. And now it was 1 times 1.005 times temperature of the heat source inlet is 350 degrees C minus temperature of the heat source outlet which is the unknown. So now if we have the value of the heat transfer 150 or 149.5 kilowatts, and we have this bottom equation, so the only unknown is the temperature of the heat source exiting from the system. So we can write temperature heat source out here is temperature heat source in minus, and now it will be Q in divided by the mass flow rate of the heat source times the Cp, which is 350 minus 150 divided by 1 times 1.005, and the result is 201.26 degrees C. So now we can get the last missing parameter, which was the temperature heat source out, 201.3 degrees C. And the enthalpy would again be T times Cp. So that was the temperature, and now the important parameter for the cycle that will interest us is the work of the cycle. As the absolute value, which is the work of the turbine minus work of the pump, which is the net work of the cycle per kilogram per second, or per kilogram of the working fluid, and now multiplied by the mass flow rate of the circulating working fluid, which here is the steam. So the work of the turbine 844 minus work of the pump 2.3 multiplied by 0.057 is 47.866 kilowatts. So now, as we had the efficiency of the cycle, we also have the absolute value of the electrical output that we get out of this cycle for the given heat source, and we can also calculate so-called utilization efficiency. But for that, first let's calculate one more parameter with the heats, and it's the heat potential or heat content of the heat source, and it will be mass flow rate of the heat source multiplied by the, well, it will be with the enthalpies, but we have a constant Cp, so multiplied by Cp and multiplied by the temperature difference between heat source inlet and heat source cooled down to the ambient temperature. So the all heat you could theoretically extract from the heat source if you cool it down to the 20 degrees C. So mass flow rate of the heat source 1, Cp 1.005, temperature heat source in 350 degrees C, temperature heat source out, heat source 0 or heat source at the ambient temperature, where the ambient temperature is 20. And this number will be 331.65 kilowatts . So this is some amount of all heat content in the heat source, out of which the cycle takes 150 kilowatts. It cannot take more because of the pinch point that we have shown in here. And because of that, the outlet temperature will have to be 200 degrees C. So you can see that the thermodynamic cycle can utilize less than a half of the heat content in the heat source, 150 from 330. And now the utilization efficiency is the work of the cycle in capital, the absolute value, divided by the heat source heat content. So it would be the Q heat source. So it will be the 47.866 divided by 331.65, and we will get that this value is 14.43%. Now later on in some next stages in some further lectures, you can also learn about something called exergy, that this 14% is the energy efficiency with respect to heat that is in the heat source. But from the point of second law of thermodynamics, we are not able to convert all this heat into work, but only the so-called exergy. And the exergy would be mass flow rate of the heat source multiplied by the enthalpy heat source inlet minus enthalpy heat source at that point 0, and minus thermodynamic temperature, that means in Kelvin, at the ambient at 0, times the entropy difference of the heat source at the inlet, minus entropy at when the heat source is cooled down to the ambient temperature. So here you can see what is the actual work potential in the cycle, but since we are not evaluating the entropy over here, so we will not tackle this in this tutorial. But if you are interested in this, please look for the tutorial Decentralized Energy Systems for the calculation of organic Rankine cycle, where this issue is handled. Now we had the parameters for the blue cycle in the TS diagram, and let's have a look at the green one. I will just add some values in here, directly in the table, just with the green. So the pressure for the green cycle at the point 1 and 4 stays the same. There is no difference. But in the problem statement we had specified the pressure at the high pressure of the cycle, which was 0.35 megapascals, 3.5 bars. So in megapascals it's 0.35, and over here also 0.35. Now the temperature at the point 1 stays the same. It's because also the condition for the saturated liquid will stay the same. So will the enthalpy and so will the entropy. At the point 2, the pressure difference is even smaller, so the temperature will be even closer to the 40 degrees C. And the enthalpy, if you can get it either from the isentropic change, where you have the pressure and entropy in some property functions, or you could get it from the saturated vapor and some specified saturated vapor enthalpy and enthalpy specified for given vapor quality, and from the linear dependency of the enthalpy with the quality in the wet steam. And anyway, the enthalpy difference here will be, as the pressure is difference is smaller, so also smaller, and it will be 167.9. So you can see a really small difference. So now the point SL, saturated liquid, it stays as condition of saturated liquid, so we have quality of 0, specified pressure. For the temperature at this pressure, so we can search for the temperature of the saturation for 0.35 megapascals, and we will get value of 138.9 degrees C. And the enthalpy can be obtained either also from some property functions from the quality and the pressure, or from the enthalpy at saturated vapor and enthalpy at some specified steam quality, and again the linear dependency of the enthalpy with the quality. And the enthalpy value at the saturated liquid in this case is 584.3 kilojoules per kilogram. For the entropy, if you are searching for an entropy also from these two independent variables, so the value of entropy is 1.727 kilojoules per kilogram and Kelvin. Now let's go to the point 3. The condition of 220 degrees remains. We have the given pressure. Since the evaporation pressure was lower, so here it's not steam quality of 1, but here it's already superheated vapor. And in the TS diagram, or from these two properties, we can get the enthalpy and entropy, which will be in this case enthalpy 2904.9 72 kilojoules per kilogram, and the entropy will be 7.323. Now in the ideal expander, the entropy remains constant, so 7.323. And from the entropy and the pressure we can get the remaining parameters, and we will see that the steam quality is higher because we were expanding from lower pressure and same temperature, so steam quality is 0.879. So already significantly better. This could be already handled by sun turbine, and the enthalpy will be 2281.63 kilojoules per kilogram, and since we are in the wet steam, so the temperature remains the same. So now in the TQ diagram, the green cycle ended up also at temperature of 220 degrees C, which was over here, but then it had some superheating. Then only took place the evaporation and the heating up from the subcooling. So actually you can already see from this that the transferred heat will be higher. So here was 0.2, which was almost the same as here. Point SL, and the 0.3 was over here. So here we had heat source inlet. The heat source pinch point would be then at this point. It doesn't necessarily need to be exactly at this line. So just let's maybe redraw it a bit, and the heat source like this. So I will just continue for everything in the green just to make clear the changes. So now we had the pinch point over here. Here would be the new heat source pinch point, and here would be the new point for the heat source outlet. The rest of the calculations remains the same. So the heat transfer between point 3 and saturated liquid will be mass flow rate of the heat source, Cp heat source, difference in temperature heat source in minus temperature heat source pinch point. Heat source in stayed the same, temperature heat source pinch point. Well, we had evaporation at a saturated liquid 139, so 139 plus the pinch point 25 degrees C is 163.9. So this is 163.9. So the heat transfer to from the point 3 to pinch point to saturated liquid is 187.1 kilowatts. Again, this works that this transferred heat needs to be mass flow rate of steam times the enthalpy difference between point 3 and SL. So we get mass flow rate of the steam for this case being 0.0806 kilograms per second. So already towards the pinch point we have higher heat input than it was the case of the total heat input for the blue cycle, and we can now also here calculate the heat input, which is 2737 kilojoules per kilogram. The heat rejected is 2114 kilojoules per kilogram. The work of the pump, since we have here the difference in enthalpies, or also if we had the difference in pressure and the density, so it would be 0.35 kilojoules per kilogram, and work of the turbine in this case is, since we have lower pressure difference, so it's lower and it's 623.1 kilojoule per kilogram. Running the numbers to get the efficiency of the cycle, we will get the value of 22.75%. So you can see almost 10 percentage points lower than before. But we have had the mass flow rate of the steam. So from that we can get the work of the cycle, and the work of the cycle in this case actually turns out to be higher, turns out to be 50.205 kilowatts. How is that possible since we have lower efficiency of the cycle? It is because this green cycle converts the heat, converts more of the heat with lower efficiency, and the trade-off between the heat and efficiency turns out to give us a little bit higher power output, and in this case of this cycle we have actually slightly better steam quality at the outlet of the turbine. So due to the pinch point limits, where we have now lower pressure, so we can get higher amount of heat into the cycle, which we convert with lower efficiency, but still the higher amount of heat overcomes the efficiency and gives us some extra power. You could run optimization to try different pressures and to see where is the optimum pressure to maximize the power output. Now let's also calculate the total heat input, where the total heat input was M steam over here, 0.08 times the Q in 2700 kilojoules per kilogram, and instead of 150 we get 220.6 kilowatts. So this is the higher amount of heat that can be converted to power with slightly lower efficiency, with significantly lower efficiency, but still ends up with higher power output. Now the heat source, the outlet temperature of the heat source will be obviously lower, and if we run the numbers with the green cycle, so we get the outlet efficiency of the air 130.5 degrees C. So this cycle could extract more heat, outlet temperature is lower. Now the overall energy content or heat content in the heat source stays the same. Nothing changes to the ambient, nothing changes to the input. So we can calculate the utilization efficiency, which instead of 14.4 will be 15.1%. 15.14%. Okay, so this was the regular Rankine cycle with the steam and with the water, and now we will have a look at the cycles with the organic working fluids. So now we will continue with the organic Rankine cycle using the working fluid Toluene. So the process flow diagram of the cycle, let's say that we will start with some condenser, followed by a pump, then we will have a look at the case with the recuperator, the recuperative heat exchanger. Following is the heat exchanger for the heat addition, evaporator, turbine, or generally an expander. Then, as we expect the vapors to be superheated, so they will go into the recuperator and back into the condenser. So let's give it some numbers. 1, 2 rec as recuperated. Then somewhere in the heat exchanger again there will be the point with the saturated liquid. 3, 4 and 4 recuperated. How does it look in the TS diagram? So the saturated liquid and vapor curves of fluid like Toluene will look something like this. And we will start with the point 1. For simplicity, no subcooling, so at the saturated liquid level. So that's 1. Point 2, going in ideal pump into higher pressure. Now let's also draw the isobars that we will have. So, low pressure isobar and high pressure isobar. So that was point 2. Now some heat will be transferred in the recuperator, some heat in the evaporator, so that we get to the point of saturated liquid. Following is the evaporation, where at saturated vapor will be 0.3. We will not assume any superheating. Now we will have expansion in the expander. In order to see it more nicely, so let's have the diagram just a little bit different, So now we have the expansion in ideal expander from 3 to 0.4. And then some of the heat is rejected or transferred in the recuperator, and then the rest is rejected in the condenser. So how much heat is transferred in the recuperator? Well, let's have a look at the temperature over here, temperature T2. Then we will have some minimum temperature difference that was specified as 25 degrees C. Which was the same for all heat exchangers. And as the heat is transferred from the fluid over here in the low pressure vapor into the high pressure liquid, so the evaporation, so the heat transfer cannot go beyond the point over here. The temperature 2 after the pump plus the minimum temperature difference. So this would be the point for recuperated. Where this amount of the heat is transferred in here. And somewhere with not so much temperature difference as between 4 and 4 recuperated will be the point to recuperated. Now if we draw a temperature heat diagram for this heat exchanger, so let's just have the high pressure, the low pressure vapor between 0.4 and 4 recuperated, and we assume that the minimum temperature difference is at the low temperature side of this counterflow heat exchanger. And why is it like that? Now we expect that the temperature heat diagram looks like this. It is caused by the fact that the vapor has lower Cp than the lower specific heat capacity than the liquid. So the vapor will need to undergo larger temperature change. So because of this, for the same amount of heat, the delta T on the vapor must be larger than delta T on the liquid side. So that is for the recuperator. So now let's put our notes in the table where we will have the points 1, 2, 2 recuperated, saturated liquid, 3, 4, and 4 recuperated. Now, what we had specified was the temperature at the point 3, which was 220 degrees C, and the condensing temperature, which is temperature at point 1, which was 40 degrees C. Also, at the point 1, as we see also from the diagram, and we assumed no subcooling, so it will be saturated liquid, so the X is 0. Then we know that for the saturated liquid point, X is 0 also at the high pressure, so over here. And we assumed no superheating at the expander inlet, so here the steam quality is 1. Now, before we go to other calculations, because we also know that the evaporation of single component fluid is isothermal, so we can say we can get the temperature at the point saturated liquid, which is same as T3, which is 220 degrees C. So now let's have a look how to get the other parameters in the cycle. Here we have enthalpy. Now let's have a look how to get the other parameters in the cycle. Here we have enthalpy entropy diagram for Toluene. You can either get those, or in real applications it would more likely be using of some fluid properties functions. And for this approach I would refer you to also watch the tutorial from Decentralized Energy Systems on this topic of organic Rankine cycles. So let's start with the condensing pressure, because here in the diagram we have over here isotherm at 40 degrees C, and at the point of the saturated vapor it connects with the isobar, where we can see that the pressure is 8 kilopascals. So the pressure at point 1 is 8 kilopascals, which is also the pressure at point 4 and pressure at 4 recuperated. Now the second pressure in the system, we had the evaporation temperature of 220 degrees C, and this isotherm at the point of saturated vapor connects to the isobar with value of 1.05 megapascals. So this is pressure P2, pressure P2 recuperated, pressure 3, and pressure of saturated liquid point. So let's fill in these into the model, into the table. So the pressure at the point 1 was 0.008, which was also the pressure at point 4 recuperated and at point 4. And the pressure at the point 2 to 3 was 1.05 megapascals. Now with the temperatures, at the point 2 we assume that it will be basically the same as point 1. Which is 40. And for the other points where we don't know the temperature yet, we know just one thermodynamic parameter. So we will have to skip that and go to some other parameters. So at point 1, we would like to get the enthalpy and entropy. But the point 1 is not on this diagram anymore, as you can see, similarly as is the case for the diagram of water and steam. But what we do have here is the point of the saturated vapor at the low pressure. And the point with known steam quality of 0.9. So because both enthalpy and entropy goes in the wet steam linearly with the quality, so we can use that to get the enthalpy and entropy at the point of saturated liquid at the low pressure. So the enthalpy at point 1 will be enthalpy at saturated vapor at the low pressure point over here, minus, and now this enthalpy, or let's say minus the enthalpy of evaporation, which is this enthalpy saturated vapor low pressure, minus enthalpy at some specified steam quality, here 90%, divided by the difference in the quality, which is 1 saturated vapor, minus x, where the x is 0.9. So the enthalpy at this point would be obtained over here. Then enthalpy for the x equals 0.9 over here. So we have something like 270, 275, and here would be something like 235 kilojoules per kilogram. And if you get the precise value, so which also could be used from some property functions for the known quality of 0 and this pressure or this temperature, so you would get value of minus 132.36 kilojoules per kilogram. Now you can see that the value is negative, but it is just the result of the reference point for the calculations in here. It does not actually matter for us, because for us what matters is always the difference in enthalpies. And if you would like to get the entropy, so we would basically use the same process just with values of entropies, or in the thermodynamic functions we could again get it as function of pressure or temperature and steam quality of 0. So let's put the enthalpy value in our table, which is minus 132.36. And if we do the same for the entropy, so we get value of minus 0.380. Now let's get to the point 2, where the entropy stays the same. So using the thermodynamic property functions, we would have the entropy and pressure to get the other values. If we don't have that, so we will get the enthalpy. We can get the enthalpy either from work of the pump, which can be approximated as V times delta P, which is delta P over density. If we would know the density, in this case approximately 848.9 kilograms per cubic meter. And we will get the work of the pump as 1.23 kilojoules per kilogram. And therefore the enthalpy at the point 2 is enthalpy at point 1 plus the work of the pump. So minus 132 plus 1.23, and we get minus 131.12. And for the quality, it's subcooled liquid. For the point 2 recuperated, we will need to first get the point 4, so we can skip it for now. And we get to the point 3, saturated liquid at the high pressure. So as you can see in this diagram, still for the high pressure of 1.05 megapascals, we don't get the value of the intersection with the saturated liquid line, but we can again have the same procedure as we had over here. We get the enthalpy at the point 3, enthalpy at the x equals 0.9, and the enthalpy of the saturated liquid is enthalpy of the saturated vapor, which is enthalpy 3, minus enthalpy 3 minus enthalpy at x equals 0.9, where the enthalpy at the point 3 is over here, which is value of 514.3 kilojoules per kilogram, and at the x being 90%, we get the value over here. So let's say something like 485, 487. and again divided by 1 minus x, where the x is in this case 0.9. So based on the precision with which we got the values, we will get the enthalpy of saturated liquid, where the precise value is 244.1 kilojoules per kilogram. So 244.1, and at point 3 we already looked at that as well. It was 514.3. Now for the point 3, we also want to get the entropy, or at least in the diagram, following process will be isentropic. So the entropy is over here. Its value is 1.1 kilojoules per kilogram and Kelvin. And for us the most important is that there follows the isentropic process to the point 4. And directly we can get also the enthalpy from point 4, which is 336.6 kilojoules per kilogram. And also we can guess the temperature at the point 4, because here we had 40, here we have 150. And the actual value of temperature over here is 90 degrees C, 90.4. So we had the entropy at the point 3, 1.01, sorry, 1.1. It's 1.102 if you use some property functions, but different property functions might get also different values. Important for us will be the difference in enthalpy, where if we keep the same entropy over here and this low pressure, we will get the enthalpy value of 336.6, and the temperature for this point was 90.4 degrees C. And finally the point 4, recuperated. It's the temperature at the, it has temperature at point 2 plus the minimum temperature difference. Which is 40 plus minimum temperature difference 25. So it's 65 degrees C. And from the pressure and temperature we could get the other property functions. Where we can guess where the temperature 65 would be over here. And the precise value is that it's about 300 to 301.6 kilojoules per kilogram. So over here would be the point for recuperated. And the enthalpy value .6 kilojoules per kilogram. So now from the enthalpy difference 3 to 4 recuperated, it needs to be same as the enthalpy difference between 2 and 2 recuperated, because it's the heat exchanger where the transferred heat is the same. So transferred heat at low pressure is transferred heat at high pressure. Mass flow rate of the ORC fluid times the transferred heat at low pressure is mass flow rate of the ORC fluid times the transferred heat at high pressure. Mass flow rates are the same because it's still the same cycle with single branch, and we end up that the enthalpy difference between 2 recuperated and enthalpy 2 is the same as enthalpy 4 minus enthalpy 4 recuperated. And you can see that enthalpy 2 recuperated is enthalpy 2 plus the enthalpy difference, 36.6 minus 1.6, so it's 35 kilojoules per kilogram. Or if we have very precise values, it's 34.9. So the point to recuperated will be at the enthalpy minus 31 plus 35, minus 139, 31 plus 35, which is minus 96.2 kilojoules per kilogram. And still this is quite far away from the range in the diagram, but if you would consider some specific heat capacity of the liquid, which is about 2.1 kilojoules per kilogram, so you can get also to the temperature at the point to recuperated, which would be 59.8 degrees C. Okay, so now we have all the important points in the cycle regarding the quality. So 2 recuperated is still subcooled liquid, 0.4 is superheated liquid, superheated vapor, and 0.4 recuperated is also still superheated vapor. So now we can calculate the parameters of the cycle, like like the efficiency, and the efficiency of the cycle with the recuperation is the work of the cycle. Or let's first start with, we have work of the pump. Let's get work of the expander, which is enthalpy 3 minus enthalpy 4, and we get that it's 177.7 kilojoules per kilogram of the working fluid. Heat input, in case of the recuperation, is the enthalpy 3 minus enthalpy 2 recuperated, which is 610.5 kilojoules per kilogram. If we did not include the recuperation, so it would be, if the heat exchanger just wasn't here, so it would be enthalpy 3 minus enthalpy 2, which is 645.4 kilojoules per kilogram. Same as this, we could also get the rejected heat. With the recuperation, it's enthalpy for recuperated minus enthalpy 1, which is 434. Kilojoules per kilogram, and if we have the non-recuperated cycle, so it would be just H4 minus H1, and then it would be just this value plus the recuperator heat, so 468.9 kilojoules per kilogram. So we can get to the efficiency of the cycle when we have the recuperation, which is work of the cycle over here. So work of the cycle is the work of the expander minus work of the pump. So it's 176.5 kilojoules per kilogram, and the efficiency of the recuperated cycle is work of the cycle divided by Q in recuperated, so we will get 27.35%. While the efficiency for the cycle non-recuperated would be work of the cycle divided by the heat input in the non-recuperated case, and it will be 28.91%. So we can see that the recuperation increases the efficiency of the cycle by about 1.5 percentage point. Not bad for just one additional heat exchanger. Now let's have a look at the, again, matching of the cycle with the heat source. So again we will have the point of the heat source in, heat source pinch point. Now let's have heat source out for the recuperated case, heat source out for the non-recuperated case, and heat source at the cool down to the ambient conditions. So the heat source was some gas at probably something around ambient pressure. And the inlet temperature of the heat source was 350 degrees C, and the ambient temperature was 20 degrees C. Now the pinch point will be same actually as both for the recuperated and non-recuperated cycle, because if we have a look at the QT diagram, so we have the heat source cooling down, then we have the working fluid evaporating at certain temperature, and let's say that at first we will have the non-recuperated case. So here would be point 3, saturated liquid. Over here we will have the minimum temperature difference. And here will be point 2. On the heat source side, here will be heat source in, heat source pinch point, and heat source out, non-recuperated case. And when we have the recuperation, so we save some of the heat input. So instead of the point 2 at the beginning of the heat input, we will have some point 2 recuperated. So actually what happens is that the recuperated case heat input is smaller, and we just don't cool our heat source to that low temperature. So the recuperated case heat source output, heat source outlet would be over here. So you can already probably see that it will not have any effect on the mass flow rate in the organic Rankine cycle. So therefore, regardless of the recuperation presence or not, with the same heat source parameters, we will get the same power output, and unless there is some limit below which we could not cool down the heat source. So the recuperation in the waste heat recovery does not have its justification. It would have justification, for example, in some case of closed loop heat source, for example, some solar application, or more or less also in case of some, for example, biomass boiler, where we would have closed cycle and where what counts is the absolute value of heat input in kilowatts and not the given heat source with temperature and mass flow rate. So now let's calculate the mass flow rate of the working fluid, same as we did before. We had the (1 kilogram per second of the heat source, and we know already from the previous calculation that Q free to saturated liquid is same as Q heat source in to heat source pinch point. So the mass flow rate of the ORC times the enthalpy difference H3 minus HSL is the mass flow rate of the heat source, specific heat capacity of the heat source, and temperature difference heat source in minus heat source pinch point. And the temperature heat source pinch point is the temperature saturated liquid plus delta T min, which is 220 plus 25, 245 degrees C, same as in the previous calculation. 45 over here, but the results should be correct. So because of the temperature levels of the heat source are the same as before, so also the heat transfer to the point of the pinch point stays the same from the previous example as 105.5 kilowatts, and just the difference in the enthalpies of the ORC fluid make the different value of the mass flow rate of the ORC, which now is the, once we know this, 105.5 kilowatts, and we know the enthalpies here, so this is the only unknown, which for this case will be at value of 0.39 kilogram per second. So you can see it's at significantly higher values than was for the water, and it's mainly because what we have also seen in the diagram, that the specific heat for evaporation of the organic fluids in most of the, basically in all of the cases, is significantly smaller than the heat of evaporation for water. So the mass flow rate of the ORC is larger, but we have lower enthalpy difference on the expander, so we will see what will it make. But before that, let's finish the calculation of the temperatures. So first, when the heat input for the recuperated case is the mass flow rate of the ORC times the enthalpy difference H3 minus H2 recuperated, and it is 238.4 kilowatts which is also the mass flow rate of the heat source, Cp of the heat source, times temperature difference, heat source inlet, minus heat source outlet for the recuperated case. And the only unknown here will be the heat source outlet, which in this case will be the temperature of 112.8 degrees C. So we have the temperature over here, 112.8. Now for the non-recuperated case, so it's MORC times enthalpy difference H3 minus H2, and it would be 252.0 kilowatts, and again it's mass flow rate of the heat source fluid, its specific heat capacity, temperature difference, heat source inlet minus the heat source outlet, non-recuperated. And from this we get that the outlet temperature would be 99 degrees C. So 99, more precisely 99.2, goes in here. So if there is no issue with the heat source fluid conditions to go down to this temperature, recuperation basically does not make any change, because the work of the cycle would still be the same. Now let's have a look at this work of the cycle. So work of the cycle is unit work of the cycle multiplied by the mass flow rate, which is over here 176.5 times 0.39, and we will get 68.9 kilowatts. And lastly, the utilization efficiency. It is work of the cycle divided by heat content of the heat source, where the work of the cycle is here. The heat content of the heat source is actually the same as it was before, because it's just parameter of the heat source, nothing changed in there. Mass flow rate of the heat source stays the same with previous problem, Cp stays with the previous problem, and temperature, heat source in also same, and temperature of the ambient also the same. And we will get that this utilization efficiency is 20.78%. Work work of the cycle and utilization efficiency does not change with if we have the recuperated cycle or not. So here almost 21%, 69 kilowatts. In the previous problem we had 15% and just 50 kilowatts, or 47 for the blue cycle, for the cycle with the expansion from directly saturated vapor. So compared to the previous water and steam, here in this case we get 17 extra kilowatts, which is more than 30% increase of the power output from the previous case. So now we will have a look at the second working fluid, which is the hexamethyl disiloxane, or abbreviated as MM. And actually most of the calculation principles will stay the same. Just let's have a look at the enthalpy entropy diagram. So you can see that the saturated liquid and vapor lines are very close to each other. So this is the specific property of this fluid, that it has very low evaporation, very low heat of evaporation compared to the specific heat capacity. And yeah, what stays the same is the temperature, 40 degrees C and 220. Also obviously temperature at the point 3, at the temperature saturated liquid. Also the steam quality at these specified points will stay the same. And now let's have a look at the diagram for the other parameters. So at 220 degrees C we have the pressure of 1.3 megapascals as the evaporation pressure, and for the condensing temperature of 40 degrees C the pressure is 0.011 kilopascals. So here is 1.3, and here is 0.011, same in here and here. Now let's have a look at the enthalpies. Where enthalpy at point 1 would be again obtained while getting the enthalpy at saturated vapor, and enthalpy at the specified steam quality of 90%, and from that linear extrapolation we can get to the enthalpy of evaporation and get to saturated liquid. Same eventually for the entropy. If we do that, the enthalpy of the saturated liquid at the low pressure is minus 121.8 kilojoules per kilogram. Now for the work of the pump. So the density of the liquid is about 746.65 kilograms per cubic meter. So the work of the pump would result as 1.0 727, so 1.73 kilojoules per kilogram. So if we add the enthalpy before the pump and the work of the pump, we will get value of minus 120.0 kilojoules per kilogram. Also, you could work it from entropy if you have property functions, where here the entropy would be minus 0.355, and here of course it would be the same. And from the entropy and pressure you would get the enthalpy and eventually also the temperature. If you do the calculations from entropy and pressure, you would get the temperature 40.36 degrees C. So the assumption of negligible temperature change is quite valid. Now again skip the point to recuperated and go for the saturated liquid at the high pressure, where we can already see this from the diagram in here. It's the point over here. Temperature of 220 degrees C, pressure 1.3 megapascals, and in the wet steam it goes from the point approximately over here, where is the point 3, to the point saturated liquid in here. So like this we would get the enthalpy, where the precise value is 278.4. And for the saturated vapor at the expander inlet, we get 375.6. Now also here we need to get the entropy, which is over here, 0.836, and the expansion line for the ideal expander will be vertical line like this, where the point 4 will be over here. The enthalpy 4.4 would be here, so you can see very close to the saturated liquid at the high pressure, and it's 275.6. So let's put it into our table. Entropy was 0.836, and enthalpy at the point 4 was 275.6. Now the temperature after the expansion is higher. In this case it would be 144 degrees C. You can see we are a little bit below 150 degrees C isotherm. Now the point for recuperated stays the same, 65 degrees C, because we still have the specified minimum temperature difference, and the temperature after the pump is approximately the same. So we have the pressure and temperature in the single phase fluid, and we get enthalpy for that, which will be 138.7 kilojoules per kilogram. It would be somewhere around here. So we have confirmed that the point 2 will always be in subcooled liquid. Point 2 recuperated also. Point 4, we have seen that the expansion goes into superheated fluid, superheated vapor, and point 4 is still, due to the temperature difference, still at superheated vapor. And now what we are missing is the point 2 recuperated. So for the recuperated heat, the relations here are still valid, and if we take the difference in the enthalpies, so we get the recuperated heat here to be higher, to be 136.9 kilojoules per kilogram. So from that we can get the enthalpy at point 2 recuperated as the enthalpy 2 plus the heat of recuperation, which now goes into value of plus 16.8 kilojoule per kilogram, and it would be at the temperature of 107.9. So you can actually see that here at this high side of the recuperator, the difference between point 4 and 2 recuperated is also quite high, so you can see that there is large difference in the specific heat capacity of the liquid and vapor. Down here, for recuperated and 2, we had 25 degrees, and between 4 and 2 recuperated, we have more than 160 degrees C. So now we can get to the parameters of the cycle. The work of the expander is almost exactly 100 kilojoules per kilogram. The work of the pump was over here. The heat input is 495.6 kilojoules per kilogram. But it's in the case of recuperation, so over here 495.6, while in case of the recuperation the heat input is 358.8 kilojoules per kilogram. The rejected heat for the non-recuperated case 397.4. For the recuperated case it is 260.5. So the work of the cycle is 98.3 kilojoules per kilogram. The efficiency of the recuperated cycle is 27.4%. So you can see almost the same value as for the Toluene. In the non-recuperated cycle, it's however quite smaller, and it's 19.83%. Okay, now let's have a look at the QT diagram. But here in this case, something else will happen, because if we follow the calculation like this, we will end up in the outlet air temperature, at least for the non-recuperated case, of in the point 2 minus 185 degrees C. So obviously that is not possible. So how the QT diagram would look like? Well, in this case, because this working fluid MM has such high specific heat capacity and low heat of evaporation, so the minimum temperature difference will need to be here at the beginning of the heat exchanger, here for the heat source outlet. So the QT diagram will look like this. So over here will be the point 2, saturated liquid, and 3. This makes our calculation a little bit different over here, because let's calculate the non-recuperated case, where we will have the heat input into the cycle will be the mass flow rate of the heat source times the Cp of the heat source and temperature heat source in minus heat source out, and we will directly get the heat source out from the minimum temperature difference in here. So in this case it will be temperature T2 plus delta T min, which means that temperature heat source out will be 65 degrees C. From that we get the heat input into the cycle as mCp delta T 286.4 kilowatts, and this is mass flow rate of the ORC fluid multiplied by enthalpy difference H3 minus H2, and from that we will get the mass flow rate of the ORC fluid as 0.578 kilograms per second. If we follow the previous assumption where that the pinch point would be same as for the blue cycle over here, so we would get the mass flow rate of the ORC working fluid more than 1 kilogram per second, but it's not physically possible because we cannot cool down the heat source that far. So here we have the mass flow rate of the ORC working fluid. We can get work of the cycle as 56.8 kilowatts and the utilization efficiency of 17.12%. In this case, the recuperation, where we would have the point to recuperate it, well, let's say again somewhere here. So here the recuperation could make sense because then the minimum temperature difference would be over here, most likely at the beginning of the heat exchanger, where we could cool down the heat source a little bit more than we are cooling it down here, or maybe the pinch point would transfer to the point of the end of preheating and start of the evaporation. That would be needed to check, and it can be, for example, your homework. So now we can see anyway that this cycle takes very large amount of heat from the heat source, but it doesn't have that high cycle efficiency in the non-recuperated case. So the work output is not that high as the Toluene, and the utilization efficiency is a little bit lower. Now at last, let's go for the R245FA. And for the R245FA, at first let's have a direct look at the enthalpy entropy diagram and find the important points. So condensation at 40 degrees C. For that we have the pressure 2.5 bars, 0.25 megapascals. Then for the saturated vapor point at specific steam quality, we will get also the saturated liquid. But now at the point of 220 degrees C of the turbine inlet, let's have a look what would be the evaporation pressure. Well, as you can see, the point 220 degrees C is above the critical point, where the critical point would be obviously somewhere around 150 degrees C, so this is too high, and the cycle would be supercritical. So for that, we will choose what pressure will we actually use, and let's choose this pressure for megapascals with 220 degrees C, so the point at the turbine inlet would be over here. Let's keep calling it as point 3. So we don't have any evaporation, we don't have any point of saturated vapor, saturated liquid with the temperature 220 degrees C. So let's draw the cycle in the TS diagram. So the vapor dome looks like this. Here we have some isobars. One isobar over here, and the other isobar would go over here. So again we go from point 1 to point 2 in the pump. Then eventually through the recuperator to the evaporator, but now there will be no evaporation that takes place, but at this selected pressure we will go to the temperature of 200 degrees C, which for the chosen pressure will be this point over here, point 3. Now there will be the expansion to the point 4, eventually some recuperator, cooling down to the saturated vapor and condensing. So again we had the point 2, some minimum temperature difference. We will get the point for recuperated, and for the transferred heat somewhere we will get the point 2 recuperated. So what we had specified, it was the temperature at the point 3, 220, condensing temperature 40 degrees C, here it was steam quality of 0, and actually because it's supercritical cycle, so we specify the pressure at the point 3 as 4 megapascals. So from the diagram we got the condensing pressure of 0.25 megapascals, so it's pressure at point 1, at point 4, and for recuperated. Then this selected pressure of 4 megapascals will be also in here, all the way to the pump outlet. At the pump outlet the temperature will be approximately also 40. We can already skip the point of saturated liquid, because nothing like that is present in the supercritical fluid, and we know that at the point 3 it's supercritical working condition. Now back to the point 1. we have the pressure or temperature, we have the quality. So from these two properties we can get the enthalpy and eventual entropy. Procedure was shown before. The values will be 252.6 kilojoules per kilogram and 1.179 kilojoules per kilogram in Kelvin for the entropy if we follow the properties in tool called RefProp. Now the point 2 should have the same entropy, or if we get the work of the pump from some density where the density of the saturated liquid at the low pressure would be or is 1306.4 kilograms per cubic meter. So we get the work of the pump as 2.87 kilojoules per kilogram, and here at the point 2 the enthalpy would be 255.4. Now, because it's high pressure difference, if we would do the precise calculation, the value would be 200 with the entropy and pressure. The value would be 255.45. Now it's 255.44, and the work of the pump 2.88. So you can see the difference is really minimal in the subcooled liquid, and the temperature at the pump outlet here would be also a little bit higher. It would be 41.5 degrees C, but still very small values. Now for the point 3, from the entropy-enthalpy diagram we could get the value of the enthalpy in here as 597.8 kilojoules per kilogram. Then we would have the vertical line for the expansion, and after the expander the value here of the enthalpy should be 528.99, so let's say 529 kilojoules per kilogram. So the enthalpy before the expander, 597.8, and after the expander 528.99, so 529.0. The temperature after the expansion would be 133.2 degrees C. Now the point 2 for recuperated. So again the temperature goes 40 plus 25, which is 65 degrees C, and for that the enthalpy would be 451.5. The recuperated heat 4 minus for recuperated is 77.5 kilojoules per kilogram, and from that we can get the point 2 recuperated, which has the enthalpy of 332.9 kilojoules per kilogram, and the temperature would be 96.1. Let's have a look at the TQ diagram of the heat input. Where the working fluid will have shape of the curve of something like this, between points 2 and 3. And for the heat source, we will neglect some possible presence of the pinch point somewhere here, but we will say that the pinch point will be, again as in previous case, at the low temperature side of the heat exchanger. And the heat source in and heat source out. So the calculation principle of the mass flow rate of the working fluid will be, in the non-recuperated case, same as for the MM. So the Q in is M heat source, Cp heat source, times the temperature difference, heat source in minus temperature heat source out, where the temperature of the heat source in stayed at 350 degrees C, temperature heat source out, in the non-recuperated case, 40 plus 25 is 65 degrees C. So the heat input is 286.4 kilowatts, and this is MORC times enthalpy H3 minus H2, from which we get the mass flow rate 0.837 kilograms per second. So for this, we can get the work of the cycle, well, the work of the pump here, work of the expander is H3 minus H4, so 68.77. Heat input in the unit values is 334.3. Is 342.3 kilojoules per kilogram. Heat rejected is 276.4 kilojoules per kilogram. Now we can have work of the cycle. As 65.9 kilojoules per kilogram. and efficiency of the cycle would be 19.2%. As the work of the cycle divided by heat input, or also it needs to work as heat input minus heat output divided by the heat input. Now for the recuperated case, it would be the enthalpy H3 minus H2 recuperated, which is 264.8, almost 264.9 kilojoules per kilogram, and the efficiency of the recuperated cycle would be 24.88%. Now from the unit work of the cycle we can get the absolute work of the cycle, which is 55 kilowatts, and the utilization efficiency then will be the work of the cycle divided by heat content in the heat source, and it will be 16.6%. In this case, the point to recuperated is around 96 degrees C, so let's say it would be somewhere here. So for this case, again probably we could transfer, not in absolute value, but for the part between 2 and 3 we could get perhaps a little bit more heat out of the heat source, because the minimum temperature difference would be most likely at this point. So here the recuperator could bring us some additional power output. So comparison of all the cases with respect to application of waste heat recovery. Let's have a look at the non-recuperated cases, work of the cycle and utilization efficiency. So this supercritical ORC, 55 kilowatts and 16.6%. Similarly, about just a little bit more, 57 kilowatts was in the case of the hexamethyl disilloxane, but at much more suitable pressures. The high pressure just 1.3 megapascals. So the utilization efficiency here was 16.6, here we have 17.1. When we apply or use the working fluid Toluene, so we get the best performance, work of the cycle almost 70 kilowatts and nearly 21% utilization efficiency. Just the Toluene has some application issues as it has, for example, issue with the lubrication of the components. And if we compare it with the steam cycle, so here the utilization efficiency of low pressure steam cycle with superheating was about 15%, and if we had the expansion going directly from the saturated vapor line, so it was even lower. Power output 50 kilowatt and less. When we have a look at just the efficiency of the cycle, So here the values are different. Steam cycle 32% with expansion from the saturated liquid. The low pressure steam cycle 22. For the Toluene, the efficiency is around 28%, so still less than was the steam cycle with the 32, but much better performance, much better power output in the waste heat recovery. And for the supracritical ORC, so efficiency of the cycle based on the recuperation 19 to 25%. So you can see that if you have just cycle efficiency, it does not need to show the whole picture for the power output that you can get, especially in applications of waste heat recovery. So this was the tutorial for the organic Rankine cycle.